So, this guy is exactly like, so you consider, so this is the conditional joint density of the Poisson arrival epochs given n t equal to n, right. Now, you consider uniform order statistics. Let u1 u2 dot un be chosen IID uniformly in 0 to t. So, now I am saying forget all about Poisson processes, you know what a uniform random variable is, right. So, if I give you some interval 0 to t, it is like uniformly throwing a dart on this interval, you throw n darts independently, all right. This is 0, that is t, okay. I am throwing darts. First uniform, let us say may land here, let us say that is u1. The second time you throw another dart uniformly independently, that may land here, okay. Then you throw a third dart that may land here, a fourth dart may land here and so on, right. This is then you throw basically n darts, okay. They land wherever they land, okay. You know the joint density of these u1 through un is easy to calculate. So, what is the density of any of these ui's? 1 over t, correct. So, what is the joint density of these u1 through un? Yeah, the product, right, they are independent. So, the joint density should be 1 by t power n, 1 over t power n, correct, that is clear, is not it. So, I can write f un of little un is equal to 1 over t power n, right, for uh, 0 less than or equal to u1 less than or equal to t, so on, right, 0 less than or equal to un less than or equal to t. See what I am saying is that if you take these, so you are throwing these uniform darts, right. So, they land wherever they land, u1 can land somewhere, u2 can land somewhere. Now, you go ahead and sort these, okay. Now, you call the u3 in this case is the smallest, u2 in this case is the second smallest and so on, right. So, this does not actually the largest does not have to be un, I do not know why I put un here, right. This could be for all we care, this could be some u13, right, I do not know, right, un could be somewhere here, right. You see what I mean, they land wherever they land, but now you order them, all right. Then you define an order statistics of this, meaning that you call the min of u1 through un as some variable, let us say y1, okay. Then you say y2 is the second min of all this, y3 the third min of all this, so on till yn which is the max of all these guys. Now, you look at the joint density of not u1 through un, but y1 through yn, okay. Now, what is that is the question, okay. It will turn out exactly like this, n factorial by t to the n. Let me just do that, right. So, now order statistics of the uniform, what I mean is that let y1 equal to min of u1 through un, y2 equal to second min of u1 through un, so on till yn is equal to max of u1 to un. So, this un through u1 to un are uniform in 0 to t, and they can be in any order, right. The first one may land here, second one may land here, third one may land here, and so on, but these y's are ordered. Y1 is the smallest of the u's, y2 is the second smallest of the u's, and so on, right. So, these y's cannot be anything, these y's will have to satisfy 0 less than y1 less than y2 less than blah blah blah, right. Now, for this what is the joint density is the question, okay. What is f yn of yn, okay. See, we can calculate this actually using a simple intuitive argument, okay. Let us say there are only two variables u1 and u2 which are uniform, all right. Let us say, so for the u1s and u2s, so if you look at this is 0 to t, 0 to t, I am looking at this is the u1, this is for u2, okay, this is small u1. I know that u1 and u2 are uniformly distributed in the square, right, independent uniformly distributed. So, the density will be what, the joint density of u1 and u2 will be 1 over t squared, right, and it will be, so it is like coming out of the surface, it is constant 1 over t square, correct. Now, if you look at, so you can see that in this region the joint density is constant equal to 1 by t square, right, f u2 of u2 is 1 by t square. If you likewise look at, if you just look at the same 0 to t, 0 to t, but you look at this is the axis for y1, that is the axis for y2, right, all right. Now, what happens? Now, remember that y1 is the min of y1 min of u1 comma u2, and y2 is max, rather only 2, right, max of u1 comma u2, correct. So, in that case the density will be non-zero in which region? Only here, right. So, if y1 is equal to u1 and y2 is equal to u2, right, you will have, so that is one possibility. The other possibility is the other way, right, y1 is u2 and y2 is u1, right. Now, both of these have the same value of density 1 by t square. So, what essentially ends up happening is that this uniform density over the square in the previous case just folds over, so to speak, right, all this mass that lying below this line just gets transferred here, right, because there are two possibilities of ordering. So, here f y2 of y2 will be 2 by t square, correct, and this is true for in this region, this is for 0 less than y1, sorry, this is for 0 less than y1 less than y2 less than t, correct. So, this is exactly what is happening with n random variables, except now there are n factorial possibilities. Let us see u1 through un can be in any one of the n factorial orders, and the joint density is of course constant 1 by t to the n, okay, and corresponding to each one of these n factorial orderings, see there is only one n factorial fraction of the n dimensional hypercube which will now be occupied in the n dimensions, just like there is only a half of the square that is occupied. In n dimensions there is a 1 by n factorial fraction which will be occupied, and the density will have to be n factorial times bigger, correct. So, same sort of a logic, like except you can't draw it, right, yeah, same logic, there is nothing different. This 2 is 2 factorial if you like, okay. So, what am I saying essentially, right. So, basically this argument can be formalized. So, we are saying that the uniform order statistic has this as the density, okay, for 0 less than y 1 less than y 2 dot 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 less than y n less than t, all right, which is the same as the, yeah. So, this expression you agree, right, this is like 2 by t square except in n dimensions, which is the same as the conditional arrival density of the Poisson point process. So, here is what I am saying, right. So, this result is saying something very powerful. You take one scenario where a Poisson process is running, I am fixing some time t, it so happens that there are n arrivals, okay. The distribution of the arrival times of these n arrivals will be statistically indistinguishable from just fixing this time and throwing n independent uniforms on this interval and looking at the ordered distribution, okay. So, if I give you two different one coming from this Poisson process, as I said, the other in another case I just throw n uniforms in 0 to t, you will not be able to tell the difference between what came from a Poisson process and what came from throwing uniform points on 0 to t. What is the probability of two independent uniforms say taking the same value? 0, correct, correct, no?
That is because of continuous.
They are continuous random variables. What is the probability of two continuous random variables which are independent taking the same value? 0, right. So, is this clear? Now, so this is the joint distribution, okay. So, moral is that, so conditional arrival epochs of a Poisson process given is the same as joint conditional arrival epochs of a point of a PP given n t equal to n is the same as the order statistics of NIID uniform random variables in 0 to t, right, they are statistically indistinguishable. So, whatever you know about NIID uniforms and their order statistics applies for these joint arrival the joint arrival epoch joint density of the arrival epochs given n t equal to n, okay, joint conditional density of arrival epochs. Now, you can calculate things like this, right, f S1 given n t for example, right, of S1 given, I will just say n given n equal to what? You can calculate this, right. How can you calculate this? So, you can actually calculate the the CDF, the complementary CDF a little easier. This is like the smallest of the uniforms, n uniforms, right. You know the for the smallest of n uniforms you can calculate what the CDF is, right. So, for example, if you look at probability that, let me just write this down correctly. Probability that S1 greater than little s1 given equal to n, right. This will simply be t minus S 1 over t whole to the n. It is like all uniforms, all the uniforms are bigger than this little s 1, right, that is what this is. Okay. This is true for 0 less than or equal to, so 0 is, this is true for 0 less than s 1 less than t, right. So, you differentiate this, I mean you see what I mean, right. From this you can, so probability s 1 less than or equal to little s 1 is 1 minus all that, differentiate that to get this, right, from this you can get this easily. Okay. So, this is an example. Okay. Now that you have the joint density of S 1 through S n given n t equal to 1, you can also get the joint density of x 1 through x n, okay, given n t equal to n. Would anything change really? The density will be the same, okay, for x 1 through x n, except that the constraints will now be so this constraint will have to apply, right. Now you this constraint will simply apply as sum over x 1 through x n less than t, okay. So you can also get conditional joint density of x 1 through x n given n t equal to n. This will just turn out to be f x n given n t. The expression will be the same, because after all the density is constant, equal to n factorial by t power n for essentially you have this, right, I is equal to 1 to n little x I less than t and 0 less than or equal to x I. So each of these x i's are non negative. Okay. So, it is the same density except that now S n has to be less than t, and of course, each of these x i's have to be non-zero. Okay. All right. So, this is symmetric. So, if you were to call x 13 as x 9 and x 9 as x 13, then I mean they are, it is completely symmetric. If you interchange the indexes of 2 of these x i's, the density would not change at all, okay, which means that the density of each of these x i's, the distribution of each of these x i's, the conditional distribution is the same, which should not be too surprising, right. In fact, we know the conditional distribution of S 1, which is the same as, note that this is the same as the conditional distribution of x 1, right, given n t of x 1 given n, right, which will also be the same, which is equal to whatever, right, I can calculate from this CDF, CCDF, right. Once I know the marginal of x 1, the marginal of all the x i's will have to be what? Exactly the same, right, because there is this perfect symmetry in this joint distribution, right. So, in the marginal densities you can easily calculate from here, right. So, the marginal conditional distributions of the xi's are the same for all I, right. So, you can just write probability. So, you can get this x I greater than s given n t is equal to n is nothing but t minus little s, maybe I should call it little x now, right. I am just copying from here over t whole to the n for 0 less than x less than t. Is that clear? See, I calculated the marginal density, right, of S1, the first arrival time, using the uniform autostatistic property, which turns out to be the S1 is same as x1, right, which is the, so the density of x1 is this, I mean you can get from this. So, but these xi's are perfectly symmetric. So, each of these xi's has this kind of a distribution, all right. Is that clear? And also you can calculate this is also something you can calculate. If you look at what is expected xi given n t is equal to n, which is the same as expected S1, right, x1 or expected S1 given n t equal to n. So, S1's density, this CDC CDF we know, right. If you calculate, what do you think you will get? Any intuitive guess? If you look at this picture, go back and look at this picture, where is that? Here, right. You are having, so you know that you have n arrivals in 0 to t, right, and all these interarrival times we said are the same distribution, correct. And so, how many intervals do you have here? 1, 2, n plus 1, correct. So, each of these intervals should be what t over, correct, and also if you want this, what will this be? Yes. So, this should be I times t over n plus 1, right, correct. So, they are all equal in expectation and distributed like so. Each of these xi's, the interarrival times, conditional interarrival times is distributed like this, like what is given in this equation. Okay. Is that clear? So, now you can calculate all this very easily. I am just giving some examples of what you can calculate, all right. So, moral of the story is that again, given that in an interval 0 to t, given that there are n Poisson arrivals, the arrival times of these n arrivals is exactly like the arrival times of some, I mean exactly like some n uniform IID points thrown on the 0 to t, okay. You cannot distinguish them statistically, okay. So, we stop here.